Now, I'd like to introduce tonight's speaker. His name is Leibig. He did his PhD with Matthias Bethke in Tübingen, and now he joined Merantix in Berlin. And it's very interesting to talk to him. He joined us this afternoon already, and so if you're a researcher and you want to talk to someone who's actually trying to get stuff to work and to apply it in clinics and like see the last bit of the road, which you often don't see as a researcher. So it's very interesting to talk to him because he knows both sides, and yeah, he has this different perspective now, but I guess he'll tell us all about it. And so without further ado, please give a warm applause for Christian.
Yeah, thank you very much, Paul, for this kind introduction. It's a pleasure to be here. Yeah, my talk is gonna. Can you actually hear me if I talk with this volume? Okay. I don't know. So, in case of questions or so, feel free to interrupt me because I don't really know what the audience is here. My talk is going to be about leveraging Bayesian, or not necessarily, but also Bayesian uncertainty information, and what I've learned from this in terms of opportunities and failure modes. So this goes back to research I've done in my postdoc times at the University Clinics Tübingen, and which took some time to get it through, but like ultimately I got invited to give a talk about this at the NeurIPS conference end of last year in Canada. And so it's not super up to date, but still very important insights, I think. So a little bit of the storyline up front. So basically, back then I wanted to apply. So I had a big vision neural network that solved a rather simple clinical task. I wondered about how can we augment this with uncertainty measures. And before diving into details, so basically I found, yes, we can actually have such uncertainty measures, and they correlate with interesting clinically relevant samples. But on the other hand side, what you would also like to get is to have a sensitivity for out-of-distribution samples, which is currently not that possible. And I'm going to relate this to more recent literature and my perspective on that. So as a short motivation, what we at Merantix and the spin-off MX Healthcare work on right now is an automation of identifying disease patients from mammography screening images. And so conceptually, it's a rather simple problem. So it's just about, does this patient have a disease or not? So is it cancerous or not? But the performance requirements are actually super high, obviously, because any error that you can make with respect to that is really catastrophic. So imagine, for example, this case here. So mammography screening is something where you really try to detect breast cancer early on in order to induce corrective measures. So such cancer cases, as you see here, that are super large are actually rather uncommon in the typical data there. And so what if we have a binary classification model that would overly confident predict that this is actually a healthy case? This is certainly something you have to avoid. And now, so this kind of problem is very, very common, and actually without loss of generality to what kind of problem you apply it, I think these insights translate. And so for now, I'm going to turn to a different task, which is what my results are based upon, which is diabetic retinopathy detection from fundus images. So you have these images that you can take the camera through the pupil of your eye, so you see the back of your eye, the retina, like a glimpse into the human brain, and you can see certain symptoms of a disease called diabetic retinopathy. And this can be a more fine-grained disease classification task. I summarized it again into just healthy versus diseased, and wondered how can we actually, besides the prediction of the network that it's either healthy or diseased, can we have some sort of uncertainty? And what does this mean from the user perspective? Well, so for each of these three samples on the left-hand side, we have the ground truth label on top, and on the density distribution plot to the right side, you see a distribution of prediction, so to say. And if the distribution is wider, we consider it to be more uncertain, whereas if it's super narrow, the network is more certain about it. And so how can we actually gather such uncertainty measurements? So one might ask, okay, for a classical neural network formulation, you basically have a softmax nonlinearity at the output of your network. This already gives you a pseudo probability, so why does this not suffice? So it can sometimes suffice, but it doesn't necessarily have to. But in order to put this into perspective, so what we actually learn here in the classical case is a single best parameter vector if we apply conventional loss functions like minimizing cross entropy. So we find the best parameter theta, so the theta summarizes weights and biases in this neural network. And now if we turn to the Bayesian perspective, we actually consider a whole distribution over model parameters, and therefore we basically have to marginalize over the posterior, over the weights, so the P of theta given X and Y, so X and Y is the training data, X the images, and Y the disease labels. And so this is the most general formulation that you can get to, but unfortunately it's super tricky to evaluate these integrals. And so when I started working on this problem, I went out and I wasn't had no clue about these Bayesian fields and what you can do in terms of the methods, and did some literature research and evaluated different approaches, and it finally turned out that there was one very important and back then very recent insight from Gal and Garamani, which is nowadays very well known as so-called MC dropout. So basically they've shown from a theoretical side that the way we train neural networks, if we do it with dropout, so dropping certain units randomly during training, that you can actually show that this, if you do it the right way, corresponds actually to performing variational inference. So it's a way of making this Bayesian formulation of the problem tractable in practice, and actually very conveniently tractable. So for those of you who know more about this, so basically you do some reparametrization, so the variational distribution is a distribution over matrices and biases, and you turn them on and off respectively depending on the Bernoulli draw you get from this random variable. And so the very high level link to variational inference is basically that the conventional loss formulation that we see in the bottom line, we have the first term is the log likelihood that we optimize for is in the top given by integrating out over the variational distribution, and the Kohlberg-Leibler divergence minimization to the right-hand side actually can be shown to correspond to the L2 regularization that we typically apply to in order to regularize our network parameters such that we don't overfit too much to our data. And now, given this knowledge, it actually turns out that in practice, in order to gather the uncertainty estimates at inference time, you actually have to do nothing more than only leaving dropout turned on at test time, and you basically draw Monte Carlo samples in order to approximate the integral, and then you can summarize the distribution of predictions by the first two moments. So the predictive mean gives you, for example, the prediction, and the predictive variance, so the width of this distribution quantifies the uncertainty. So the higher the variance, the more uncertain your prediction is about. And since that was known, there was also lots of follow-up methods published that often claiming like, okay, we need something that is computationally more tractable, but actually, so I applied this to a 14-weight layer Bayesian convolutional neural network, so fully Bayesian throughout, to 512 square color images, and for drawing 100 Monte Carlo samples, like with a naive GPU-based implementation, it takes about 200 milliseconds to approximate the predictive posterior. So that's actually very feasible to be applied in practice for medical problems. So now the question is, what can you actually do with that? And so this following scenario here is motivated twofold. First of all, it's interesting for practical use cases. And second, it's a good scenario in order to evaluate that you can actually, to what extent you can trust the uncertainty measures, because a priori this was not really clear whether these what you get out of this is actually useful. So it goes as follows. You have an input image, feed it through this Bayesian neural network, gather your predictive distribution, and then in case you have a high uncertainty, you refer the data and decision to an expert, because you say, okay, can't put the decision in place here. Otherwise, if for low uncertainty, you simply accept the neural network's decision, and with that you can build complementary systems that get the best of both worlds, so ML and human experts. And you can use this scenario in order to check whether the relative scaling of the uncertainty values actually makes sense. So binary classification problems typically evaluated with a RC characteristic, which you see on the left-hand side. And so the more this goes to the top left corner, the better. And you see here like 4 different curves. The turquoise one is like on the whole test data set. And the subsequent ones is if I take out the 10%, 20%, 30% of the most uncertain samples. And whenever I do this, I get a consistent improvement in RC characteristics, surpassing also the requirements of health organizations that one has given for this kind of problem. And important to notice that actually the absolute scaling of uncertainty values, so the calibration of them, is not important for this task to work out. It's only the rank ordering that you need to have sorted out correctly. Now in order to, this was like a single example, but let's open the box a bit more and do more experiments on checking whether this is also holds true for different scenarios. So first of all, going from left to right, I do it not only for like these 3 samples here, but I screen a whole range of thresholds of my referral scenario. So I sort out more and more uncertain data and summarize each ROC curve by the area under it. So the best possible value you can get would be 1.0. And so the more data or the less data I retain in order to classify automatically, the better the performance gets for the MC dropout case. And I compared this to random referrals, so just considering any of the samples as uncertain, and likewise to Gaussian processes, which is a sound way of doing probabilistic inference. And both this as well as the standard dropout measure didn't show as good as a generalization performance. And next so we've seen this outperforms other straightforward alternative methods. Here I checked 2 different networks by formulating 2 different tasks, so earlier and later disease onset. And in addition, so this is on the left-hand side and right-hand side, so there's many experience behind this. And on the first row, so the Kaggle data is actually from, the test data there is from the same population as the training data came from, whereas the second row is the Messidor is a data set that is completely independent, so you see the same qualitative behavior there. So this is a sign that this actually is robust to see these effects. So this was a good indication that the uncertainty values we get out of here are actually useful in practice. However, with that only, one didn't really know what it would actually mean. So I wondered, okay, what is it that actually characterizes sample to carry high uncertainty? And in order to visualize that, I came up with a smaller toy problem that actually comprises all of the key aspects that we also have in the high-dimensional image case. So it's, again, a binary classification problem. It's not separable, so the 2 clusters, so the blue and the green dots slightly overlap. So it's sufficiently hard. And in order to get the best solution, we need a nonlinear function to separate that. And so on the left-hand side, you see the heat map for the standard neural network formulation, so the standard dropout. In the middle, the predictive mean, so the prediction of the Bayesian neural network. On the right-hand side, the uncertainty map, so the variance of the Bayesian neural network. And what we can observe here is that the variance, interestingly, is high along the decision boundary of the classification problem and spreads out towards extrapolating regions. So to give you a bit of like a hand-wavy explanation why this actually makes sense, that it is like this. Because intuitively, like very initially, and many people have here, including us, the intuition that you would have also high uncertainty, like basically far away from the data point that you trained on. And why is this actually not the case, and why does it make sense to look like this? For that, let's consider the following scenario. So basically, let's define the contour of the maximum uncertainty in terms of like where can I not decide between the two classes, so where's the probability 0.5. If I resolve this, then I get basically in the linear case, the equation for the separating hyperplane, and in the nonlinear case, it's all very similar except for that the separating hyperplane can be nonlinear, which is captured by this f here. So it's actually such that in the classical perspective, we model with a single best parameter vector, we model a single separating hyperplane. Whereas in the Bayesian case, if we have a distribution over the thetas, we basically get the distribution over these separating hyperplanes. Yes?
Where does this come from? Is this from the softmax layer, or?
Yeah, exactly. So basically the P of, so this guy here is the sigmoid function. So this would be for a binary case, and in the general case, it would be the softmax layer. So that's the output nonlinearity of your neural network, and you basically always have this in place. So even if you have a deep network, if you formulate as a binary classification problem, you end with a logistic regression layer. And I basically just take a look at the last logistic regression layer, and basically going back to this, why does it then, in this case here, we have a two-dimensional feature space, so x1, x2. Why does it look nonlinear? This is basically the back projection of the nonlinear feature transformation into the input space. So with this, we can have kind of a mental model for why it makes sense to look as such, and can come back to the key characteristics, how it looks like in the two-dimensional case. Basically, I want to like grasp two key points here, and then check whether these observations also hold true in the high-dimensional space, having this mental model in mind. So one key point is, okay, we have high uncertainty along this separating hyperplane. And second, it looks as if we have a data point far from the data we care about, we would like to have high uncertainty, because that would be the initial like big cancer case that we want to flag up. Here it looks as if the uncertainty is low. If we are here, it could be high if we are here, but it basically depends on the task, on where we are so it's not isotropically high far away from the training data. So I did a couple of experiments in order to check these like qualitative observations. So first of all, is it high in close to the decision boundary? For that, I leveraged basically extra information I had in this Kaggle competition dataset, whereas I had just trained the models for the binary scenario, that it was originally actually a 5-class classification problem, and the disease labels go from 0 is no disease present at all to mild, moderate. So basically, they are ordered by disease severity symptoms, and so neighboring classes tend to have similar. So this is rather like smooth transition. And on the left-hand side, you see the mild DR detection task. On the right-hand side, the moderate DR. So basically, on the left-hand side, everything 0 is healthy and 1, 2, 3, 4 is diseased. And on the right-hand side, I moved this boundary in the label space to distinguish between 0, 1 and 2, 3, 4 respectively. By using this information, I then checked, okay, now if I have this referral scenario, basically So here the x-axis screens the threshold of uncertainty. So how uncertain do the samples have to be in order to be referred to a physician's opinion, and check the proportion of the fine-grained label information in this data set. So we see here basically for very uncertain samples, here we predominantly get healthy and so class 0 and 1 samples rejected. So this is the ones that in label space live close to the decision boundary. So an indication for being difficult. And if we move the decision boundary, so the healthy disease boundary in label space, then the most uncertain samples contain ones, first only ones and then twos respectively, which is an indication that what we see in the two-dimensional scenario also is qualitatively the case in the high-dimensional image space. Another experiment also in order to support this is that in this data set there were like the image classification was based on a single image, but every patient had 2 images because of the 2 eyes, and there was a certain fraction of patients that had disagreeing labels, so they had the left and right eye were in different disease states, and so competition participants had actually made use of this correlation where it was not disagreeing in order to boost performance, and I flipped the coin and checked, is it actually that the ambiguous patients where you have different disease states left and right, so it's more like on the borderline between overall the patient is on the borderline between being healthy and diseased. Is it predominant? Are the ambiguous patients more frequently represented in the referred dataset? So do they carry a higher uncertainty? And these plots basically show that this is actually the case for the analyzed scenarios. So there's basically to sum up so far, so it seems like there is clinically relevant samples that are difficult and carry a high uncertainty, and we can also make use of this in order to boost the performance. Now let's come back to this case of the big cancer that we would like to flag, because in practice we train such an algorithm and you want to get high performance and we have some test data and measure that, but we never know what is the future samples going to be that we get during deployment, and we have to make sure that we don't put out like garbage predictions here. So therefore this interest in the out-of-distribution detection. And here, so the two-dimensional case suggests that it can have high uncertainty but doesn't necessarily have to. And in order to simulate an experiment in the image cases, I took as in distribution all the Kaggle images, all the fundus images, because that's what I've trained on. And as a rough sample from the out of distribution, I took all of ImageNet validation, so 50,000 images with all sorts of natural images in there. And basically plot here is your density plot of the uncertainty, Kaggle messenger, so green and blue is fundus images that have a certain uncertainty population over the test set, and the reddish distribution is ImageNet. And we see, okay, these distributions overlap, so you cannot separate apart out of distribution samples from in distribution samples based on uncertainty. And as a rough qualitative contrast experiment, one could argue, okay, what you actually have to do is you have to model that, you have to do density modeling on your training data distribution. So what I did, I basically ablated the classification head from the network and took the last 512 dim feature vector and trained a generative model on that, so plain old-fashioned autoencoder, and took the reconstruction error to measure the distance of a test sample from the original data and take this as an anom or out of distribution score. And here you see that it's not perfect, but the red distribution tends to is less overlapping with blue and green as in the uppercase.
Did you freeze the encoder weights when you trained the decoder? So this is the untouched classification model, or did you train everything again from scratch?
No, I freeze them.
Okay.
I just took it as a feature representation. So there's a lot of room to actually optimize that. It was just for showing that in this direction you get a qualitative difference because you'd like,
makes sense.
yeah, I mean, it's not necessarily the case that these features, so they have a good grasp on what an image is about, but it has been trained on this discriminative classification task beforehand, so who knows what kind of information is actually lost. So to get a good generative model, I would rather go back to the original image space and train throughout.
How unbalanced are those data sets, like KLT versus you?
I think it was around about 80 something, 83% healthy, 17% diseased. In one of in the early disease detection task, and on the later on you get more diseased samples. But you can take. It's generally a bit nasty, but the RC evaluation is invariant to class imbalance. So if you would have a different relation there, you would still get the same results. In terms of getting to the performance at all, yes. I mean, so what I basically did is I gave minority class errors a higher loss contribution. And yeah.
So in that sense, like the 70% power data set of like the diseased ones were the ones that had like more impact in loss, or how did you?
Yeah. You can do that either by scaling, like knowing that it is a minority class sample and giving the loss a higher weight, or you can simply show more of the diseased ones via data augmentation or so. Yeah, and another, I mean, generally the like getting this whole thing to train wasn't easy because I had a deep network and I introduced dropout everywhere. So it's rather uncommon to have dropout, for example, in conf layers.
There's no common rule of where to apply dropout, right? It's pretty fussy in the literature, so everybody just does what they think is right, but there's no theoretical background on where to put the dropout. Yeah,
not really. But best practice is to apply it only to fully connected layers. Yeah. At least most often. At least that's in my experience. Yeah.
How did you tune the dropout rate then? I mean, because if you put it too high, your model gets.
I basically started with a low dropout rate and increased it as much as I could to make it as Bayesian as possible.
Okay, and then just make sure the model is still learning something, and when you saw that the training performance decreasing, you stopped.
Exactly. So basically, it was a compromise of having as highest dropout as possible and regaining the original performance without dropout. So basically, that's the reason why you see that these curves start out at the same origin. Like this point here is for all methods the same performance.
Did you use different thresholds for the different dropout layers?
No, it's a global dropout probability. You could, but yeah.
So you use the same dropout rate for the fully connected and the convolution layers?
Yeah. At least I think so. I would have to double check to be sure, but there's anyways just it's mostly conf layers, some pooling layers, and concatenation, and there's only the logistic regression head is fully connected.
Yeah, because usually when you have really low dropout rates, usually if you apply to convolutions.
Exactly. Yeah, it was 0.2. So.
Okay.
Yeah.
Concerning the dropout rate and then the posterior uncertainty, did you notice any sort of relationships there? So, for example, if you have a really low dropout rate, is the posterior distribution pretty tight, or is there any sort of relationship there?
So, because it was relatively tricky to get to this performance and train it at all, and so I did not really analyze this because I could only get to 0.2 dropout, and I didn't see a point to compare this to 0.1 or so. But Yeah, so another thing that influences the posterior approximation is the number of dropout samples you draw, and there I didn't see a big difference.
But it's a good point now. For you it wasn't crucial because you only ranked them and wanted to sort out the very uncertain ones. But when you want to show it to the radiologist and the calibration of the uncertainty becomes important because it has a certain meaning for this doctor, then you would want to know the factors that calibrate your uncertainty and I think the dropout rate. But then you can still try to learn it or something.
Yeah, so there's two answers to that. One is yes, you can there's extended work on that. You can basically learn the dropout rate and also apply it differently to different parts in your network. Generally, I disagree that I don't think it's important to understand the exact posterior behavior because it's a crude approximation. Then there is no interpretable scale to that. So therefore, I came up with these experiments where you just rely on the rank ordering. So you only have to have an example that is really more uncertain should have a higher uncertainty. That should suffice. And then there's much more parameters even in there. So basically, if you look into the original derivation, where you have the relation between variation and inference and this training scheme, and there's also a relation to Gaussian processes. And basically, in the Gaussian process world, you formulate your prior assumptions and covariance covariance kernels, and how this translates is basically that if you have a different architecture or different non-linearities, this also has an impact on the posterior. And I think in practice, one is really constrained to come up with the right architecture generally for the problem, and it's complete overkill to engineer the right posterior there because nobody knows what the right one is because already a Bayesian logistic regression is actually not analytically tractable. So if you look into the literature, it's all just approximations. It's either Laplace approximation or variational inference or Monte Carlo sampling.
So from an implementation perspective, you usually use dropout layers, right? And don't these just drop out activations instead of weights? So if I have dropout layer after a conf layer, I'm actually dropping out the activations and not the actual conf weights. Is that right?
I would have to look into the code. How did that?
Channels, right? When you drop
Complete
out
channels?
For convolutional layers, I thought, the way I understood it, for fully connected, you drop out neurons basically. For convolutions, I thought it was that you drop that you said to zero a full channel.
Oh, for real?
I think I did.
But I'm not 100% sure.
We can have a look at the code later, but I think I dropped individual neurons. So both perspectives are actually valid. So if you would drop a whole channel, you would drop an entire filter. And if you drop individual neurons, you basically just certain realizations, instantiations of a neuron that shares a filter kernel with others. Okay, so up to this point, I've basically shown, okay, it works. You can get performance improvements. We know now that we have these two qualitative interpretations, so where it works and where it doesn't. So difficult samples, yes. Out of distribution samples, not necessarily. Now, if you check what other people have done, there's actually quite some literature that also reports beneficial results on out of distribution detection. And I wondered, okay, what's actually going on here? So why do these? Because I think they do it right. So why do they see these effects and I'm not, or not? Where's actually the difference? And then so here's a couple of points on more on that later. So one thing is sometimes only the mean uncertainty is reported instead of individual the structure of the distribution. So basically, and yes, so we have some we saw that in extrapolating regions of the decision boundary, there the uncertainty is high. So if you have some of them being higher, then the mean uncertainty over the test set goes down. So you get a positive result, even though it's something you shouldn't rely on in practice. Then the second point is maybe a bit more hand-wavy, that sometimes like the in and out of distribution data sets actually are kind of similar. So one typical case is that people compare MNIST versus not MNIST. So one is handwritten characters, the other one is handwritten digits, and the other one is handwritten characters. So like basically something that is made up of similar features. So some strokes of handwritten stuff, and then it may be that actually the out of distribution samples actually by chance fall on decision boundaries, and there we have the high uncertainty. Then a more crucial point is that if you have more classes than only two, you have more decision boundaries, and therefore more of your of the input space volume covered with higher uncertainty. Next, then, if the in-distribution task is easier, like MNIST is a super easy task, then you get lower uncertainty there. Medical imaging tasks tend to be more difficult because they're more blurred in terms of like the actual result. It's not as easy to classify, often because the classes overlap more strongly. And lastly, if you go to, so basically in this two-dimensional setting that we had, so this one here, so x1, x2. Now imagine you would get a third dimension. Now you can basically take then you would get a plane instead of, let's imagine a linear problem. So you have a line cutting through this. And now we get a third dimension. Now we have a plane. And we can actually rotate the plane and still get the same classification performance. So the more dimensions we have, the more flexibility we have in order to fill in separating hyperplanes. And now if we model in the Bayesian perspective from many different possible solutions, then we get a much more blurred version. And therefore, this can have an influence where basically this gives a continuum that maybe in some situations you observe out of distribution detection to work.
Does it mean that the hyperplanes basically try to solve the same thing as labeling would do in reinforcement learning sense? When you try to separate data sets if they are not classifiable in the given labeling system or so, and you try to specify it more in detail?
I'm not sure I understood your question.
Because as I understand it, hyperplanes are basically the idea they have like a new layer on top, which I don't know separates the output basically in a new dimension or in a new perspective of the dimension, depending on how the plane looks like. So for me, I think for me currently it's unclear whether it's like, for example, just layers on top of each other, or planes that have like the same projection of the same points basically, but with different separators in between, or whether or not they are just, I don't know, like a 3D description of just take this camera perspective in the 3D volume, for example, or something. Like, for me it's like unclear how the hyperplanes are constructed basically, I think. Or what they do specifically.
Yeah, so basically, the final point I'm gonna get to is basically, I think it depends, so that the hyperplane is basically the function you learn because you have a classification task. So the classification task in the most simplest setting is, let's say it's binary 2 classes, and all you learn is to divide your input space in 2 half spaces. And basically the bordering is the hyperplane.
Okay, so the divider basically between like type A and type B.
Exactly.
Basically.
Exactly. And therefore it's unreasonable we tend to learn simple solutions because we regularize, etc. So we want to learn smooth functions. So at the end of the day, the hyperplane will be kind of smooth. But here, like results from like half a year ago or so. So what we see here on the left-hand side is basically a 2D latent space visualization of the uncertainty for MNIST. So we have a relatively high-dimensional input space. We have 10 classes, and now we can observe certain aspects. So white is high uncertainty. So we see, okay, between the class boundaries, the uncertainty is high. But in comparison to my more simpler binary classification problem, where far away from these colored clusters, the uncertainty is high. It's a bit more like complicated in terms of the structure. And now, if you look into Hendricks and Gibbel, this is like a paper that came up with lots of different, like basically a benchmarking, proposes lots of different benchmarking dataset pairs of in and out of distribution. Then I would argue it depends on where the out of distribution dataset samples reside in the space, whether you succeed or not in terms of performance. And this is also what one roughly sees if you look at the results tables, that there's a much bigger difference between the dataset pairs as between the methods. And here's an exemplary comparison of two different uncertainty methods applied to the same problem. So MC dropout on the left-hand side, which is what I had used, and inhibited softmax on the right-hand side. And you see that the uncertainty landscape is qualitatively very similar for the two different methods, even though they approach it quite differently. And
inhibited softmax, it's like a softmax entropy, or?
It's basically they add an extra unit to that does nothing. Basically, is something like a background class, and that basically it goes into the denominator of the softmax, so it shrinks everything down. And this qualitative idea actually was also like it's different, but generally, like roughly, there's some work on. And I also had this idea once, or what other people have called it temperature scaling. So the reason, like if you think about it naively, one of the reasons why you don't get uncertainty in this region here, for example, is basically if the logits let's just take the sigmoid function, the logits that go in there, if they are basically either of very high or very low activation, then you are in a saturating regime. And even if the variance is high, so even if there's lots of uncertainty, it's all gonna end, because of being fed through this nonlinearity, it's gonna be squashed into zero or very small variance. So I thought, okay, what can you actually do? Well, you can basically manipulate the input such that it gets into the sensitive regime of this nonlinearity again in order to make this fluctuation come through. And basically, so here on the right-hand side, you basically see exactly the uncertainty over the logits. And it's kind of a complementary picture. So there you see, okay, it's actually, here we have this like far away from the training data, and you see it's huge activations. So the scale here is completely different. It's like up to 24, and here it's 0.56. So I was actually quite excited when I saw this, and I thought, okay, so somehow the information is in the network, and you can kind of get this out, and then the problem is solved. But what I actually oversaw a bit back then is that you kind of still have, even in the logit space, and this makes sense because the discriminative training information is propagated through the network stack, you still see this like a slight dependency on the direction, on the main direction of this separating hyperplane here. And this makes it actually very hard. So I try to come up with combinations of the two, like input and output uncertainties. So this and that guy somehow mingled together in order to basically capture all of what we want to achieve. But this is quite brittle, actually. An alternative way is maybe a bit more like less empirical and more rationally driven is, okay, if you think, what if we basically explicitly make it part of our training objective that we would get a thinking for a moment not in terms of these distributions, so basically calibrate the network output to give us 0.5 probability for binary classification problem if we are far away. So what we have to do for that, we have to make the logit 0. You can do that if you model the distance from your data distribution. So basically having this modeling of the data in distribution and classification task both in at the same time. This you can do if you use kernel functions that are like where some like distance measure goes in. Here you see some examples for Gaussian processes and radial basis function neural networks. Here I found that you can probably get this going right, but again it's a bit unstable because you see here that it swaps a bean. It's not necessarily 0.5 here, but it tends to be like on either or the other side, possibly. Okay, so these were like few ideas how you could deal with that in principle. Now I look on what could you actually expect if you would do this generative modeling aspect a bit more, if you would invest more time into that. So there's one nice paper last year's ICLR where they actually also combine discriminative and generative modeling, which is very promising. But one interesting observation there is that there's again like a weird dependency on what is your in and out of distribution. So if you train on SVHN, but out of distribution is cipher 10, you get good out of distribution detection performance. If you flip it around, performance drops. So it's kind of what this maybe depends on, but also like Naslik and al. Have found, which with this paper, which made quite a big buzz, that maybe generative models aren't there yet in terms to be used for out of distribution detection per se. Okay, with that I want to conclude. So I'd say yes, Bayesian uncertainty is actually practical in order to be applied in a medical setting, as long as you are aware of what you can use it for and what not. So you can use it for performance improvements and for the combination for this referral scenario in order to combine human and ML expertise. Also an interesting use case is active learning. So for example, we have collected large amounts of data, and it's interesting for us because annotation costs money to annotate what is interesting for the models. So, and because you have the high uncertainty in extrapolated directions, this is exactly where you want to get your discriminative function to be better. And for out of distribution detection, one should be careful for now. And that's it. Yeah, with that I would like to thank you, and also my co-authors and colleagues and friends from Tübingen and the Merantix team, and thanks for being here.
You want to take the questions yourself? Maybe that's the easiest way.
Yeah. You mean here we see the uncertainty landscape in the latent space, and so this was independent models, and so taken from the literature with different uncertainty methods. So I would, this is an indication that it does, yeah. because of like different initializations and ending up a bit differently. Yeah, yeah, but I think yes, I guess you end up with different like VAE solutions, but the uncertainty can still look qualitatively the same, right? Because this is what we visualize here. It depends on what you mean by does the latent space look the same, I guess.
If I remember correctly, the experiments are made with images 520 by 520 resolution. Do you have experiments with lower resolution or higher resolution? That's the first question.
Yeah. So here my goal was not to like get super high performance or so. For me, my goal was to understand these uncertainty measures. And I basically took these values from the results of the Kaggle competition. And there people have experimented with different resolutions and found that so up to a certain extent, higher resolution helps, and then at some point it saturates. I don't have the exact numbers in my head now, but this basically was a top scoring solution that I re-implemented and started off from.
Okay, the second question is on slide number 14. If you look at the standard dropout, the most left, the best performing one, it looks like about 10% of the data points has high uncertainty. So how this is possible if 10% of the data points has high level of uncertainty? The model to perform better when you decrease the data and exclude the data with the most uncertainty above this limit, because the limit there was 50% and it increased quite a lot. I mean, I think it was on the few previous slides.
Yeah, so you basically want to relate this with the referral scenario. Yeah. So first of all, the standard dropout is not the best performing method. So it's actually, so very first of all, this is on the medical imaging task, these performance results, and not on the toy example. So the 10% may look different. Then standard dropout is basically the well-performing one is the Bayesian MC dropout, the blue one. The standard dropout here is the orange curve. And now basically, let me try to understand where you're hinting to. So basically, let me explain the referral task on this example. It would basically mean that I remove those samples that reside on the highest uncertainty regions, like let's say 10%, and then, okay, you say that the performance should go up. Yeah, okay, I see your point. Yeah, then this.
Because here what we can see that the less data, the better performance.
Yeah, yeah. I guess this is because there you have a difference between this problem and the medical imaging task. So it's really more like the uncertainty values for the whole test set are these here for the medical imaging task. So basically for me as a I've seen these images, but I could not judge whether the disease symptoms are present or not. I simply have to trust the labels of the physicians. And my feeling is that the decision boundary is a lot more blurred in the medical imaging task. A lot wider than.
This means that TikTok's not imply that.
I'm not. I want to relate this here qualitatively, not quantitatively. So there is. the exact, like how long it takes to fall off, let's say in this direction, depends basically on how much your data clusters overlap in the logit space, basically. And this can be very different in the medical imaging task, where you have like 512 dimensions. Here we have 2. The only claims I make is in terms of these very, like, just these 2 coarse-grained statements.
But isn't that like totally dataset dependent in that case? Because as you mentioned, I don't know, if you compare, for example, these 2 pictures between standard error and predictive mean, that's only the case that one can outperform the other just because of the grayscale areas in between and how they are interpreted. Because standard dropout will always like reinforce like logarithmically, versus the other one, which will lead to, I don't know, like not so rapidly decreasing gray areas or areas that are in between, right? Before it's like classified as being blue or green in that case, right? So in that case, you could, I don't know, either order the data set in the sense that you have like those variants where you're unsure, but the physician was always right, put them at the first of your data set while training. Or you could, like, I don't know, increase the randomization of classifying them as a separate data set and randomizing them so they have like 50-50% chance of occurring or something during the training phase. And then you would have like the same performance with both algorithms probably, right? Or both methods of classifying.
So, I mean, there's still always a dataset independent
Of course.
difference here, which is basically, if you look...
I'm just mentioning because I think the training phase here is really relevant because you have so many data points that are in between that actually are unsure or not classifiable in one region alone, right? And that's why the predictive mean can outperform the standard dropout in that case.
I wouldn't say so, because so correct me if I didn't get you right, but no, but let me point out, I mean, in the left-hand side, we have a single solution, and this is much more prone to overfitting than and this will be more smeared out. Even if you have a completely separable problem, it's more smeared out than not.
So standard, of course, standard dropout is more prone to
Yeah.
overfitting in that case or underfitting in that case.
Yeah.
I guess it's clear.
Yeah.
Have you checked what the uncertainty look like for some adversarial examples?
No, I didn't. So, but there's some. I'm not aware of medical work, but people have tried to use adversarial training to basically manipulate the certain regions of the input space with different ideas in mind to basically play with the decision boundary. Yeah. Sorry, I think there were a few more before you then.
So you mentioned in your 2-dimensional example that uncertainty doesn't go down if you go further away from the data clouds towards like top right and bottom left. But in the MNIST example that you showed, this seems to be the case. Maybe if you show the MNIST. So there, uncertainty goes up when you, for example, go to the bottom right.
Yeah, this was basically one of the so one of my points here was that we have here a higher number of classes. So I wanted to make sense of both worlds, and so the functions you learn with 10 classes are more complex than with only 2, and then they can tend to wrap around or so. So therefore, yes, you have basically here a lot more uncertainty. So therefore, this can explain why sometimes the results seem to show that this actually works. And I wanted to contrast this against, but it's basically, it works better than with only 2 classes, but there's no guarantee for it to work. So because here, it wouldn't work. Sorry, there was one more here. Yeah.
One slight drawback of your method is like that you have to train with dropout, so you have to use dropout. Do you think it would be possible to just use your method without using dropout during training? Just using dropout nonetheless, even though you didn't train with using dropout? I mean, then your model will probably generalize more poorly, but maybe that would be still reflected in your uncertainty.
Yeah, so there's work on basically whenever you have some sort of stochasticity in your system, you can interpret uncertainty measures into it to different degrees. So there's a work for it that shows similar stuff like this for dropout for batch norm, driven by the practical argument that nowadays maybe for some architectures people rather tend to use batch norm instead of dropout. So there you have stochasticity because of the moments you estimate and so. Then I think there's even work on showing this for stochastic optimizers per se. And not directly like answering your need, but people have also like basically said, okay, let's accept that we need dropout during training, but we want faster inference. So they train an auxiliary network that basically learns the mapping of the uncertainty such that you don't have to draw Monte Carlo samples at inference time. But I actually made a point that you might need this for like real-time applications in some embedded system or whatever, but there's no need for that. In a medical diagnosis can wait a few seconds until it's there.
Sorry to interrupt. Maybe it will be okay to take the rest of the questions offline.
Sure.
The pizza's getting cold, and no one wants that. So I think Christian is going to stick around for a while. We can ask him lots of questions still. And so let's thank him again for now.